The rotational energies of symmetric tops are further divided into prolate and oblate symmetric tops. We first look at the prolate symmetric top, which has I sub A less than I sub B, which is equal to I sub C. There's a total angular momentum quantum number J that it determines the quantized total angular momentum. Total angular momentum is equal to the square root of J times J plus 1 times H cross. There's an additional quantized value. Recognize that a molecule is not spherically symmetric. It can rotate in three different ways. However, symmetric tops have one unique rotation and two equivalent rotations. The unique axis is called the figure axis for the molecule. It turns out that the component of the total angular momentum in the figure axis is also quantized. Since the definition of the figure axis depends on the molecule, it is molecule dependent. It can be considered a sort of molecule-defined z-axis. This is different from the absolute spatially defined z-axis. The letter k can be used to indicate the quantized figure axis component of the angular momentum, which follows the same rules as component z uh, of the angular momentum. L hat sub z psi molecule is equal to k h cross psi molecule, where k is equal to 0 plus or minus 1 plus or minus 2 all the way up to plus or minus j. Equation 14.15. Note that k is bounded by j just like m sub l is bounded by l. Figure 14.6 shows the differences in the definitions of the figure axis component and the z component of the angular momentum. Angular momenta about both axes are quantized in symmetric top molecules. Equation 14.9 and 14.15 are both applicable to the rotations of symmetric top molecules. It can be shown, we omit the detailed derivation here, that the total rotational energy of the prolate symmetric top is quantized. The energy in terms of the quantum number j for the total angular momentum and the quantum number k for the figure axis component of the angular momentum has the following expression. E of rotation is equal to b times j parentheses j plus 1 parenthesis close plus parenthesis a minus b parenthesis close times k squared. Equation 14.16. In this case, the energy of the rotating molecule depends on the two quantum numbers. Just as for linear molecules or original 3D motor, the energy is not dependent on the z component of the angular momentum. It is dependent on the figure axis component because A is always greater than B. The second term in K is always positive. K squared is always non-negative and represents an increase in the energy of the rotating molecule relative to the diatomic spherical top molecule. For an oblate symmetric top, a very similar expression for the quantized energy of rotation can be obtained, except that now the lower of the two moments of inertia are equal to, and the largest is the unique one. But a similar derivation, again omitted here, uh, leads to the similar expression E of rotation is equal to B times J parentheses J plus 1 parenthesis close plus C minus B parenthesis close K squared. Equation 14.17. In this case, since C is always less than B, the second term in the equation 14.17 will always be negative, and the second term contributes to the overall decrease in the rotational energy of the oblate molecule relative to a diatomic or spherical top molecule. Section 14.5. Selection rules for rotational spectroscopy. Given an understanding of energy levels of molecules due to various types of motions, it is a simple step to consider the spectroscopy involving those motions, because spectroscopy involves a transition from one energy level to another. Spectroscopy uses the Bohr frequency condition, originally proposed by Niels Bohr in his theories of the hydrogen atom. This was discussed in section 14.2. Since the energy levels of rotations for simple molecules are known from the treatment above, determining the change in energy levels is straightforward. Classically, light is an oscillating electromagnetic field that will interact with other oscillating electromagnetic fields, much the same as two magnets or electrical charges will interact with each other. Consider a molecule whose only motion is rotation, so that we can consider the pure transition involving only rotational quantum levels. Such a rotating molecule does not provide oscillating electromagnetic fields unless the molecule has a permanent dipole moment. If it does, the rotation will provide an oscillating electromagnetic field on the order of light's oscillating field, and then the light and the molecule will interact. Figure 14.7 illustrates this interaction. In order to observe absorption or emission of light due to pure rotational transitions, the molecule must have a permanent dipole moment. The phrase pure rotational transitions is crucial since several types of motions of a molecule can interact, mix, and seemingly violate such simple statements. We will continue to consider some examples later. The presence of the permanent dipole moment is sometimes referred to as a gross selection rule, since it relies on a general property of a molecule rather than the specific wave function of the molecule. More specific rules of selection are based on wave functions and will be considered shortly. The gross selection rule is general and considers a general property of the molecule. What about specific transitions between rotational quantum levels? Can any two rotational wave functions be involved in a transition, or is there a restriction on the wave functions that can interact via absorption or emission of a photon? There is indeed a restriction, and it has to do with the fact that photon has angular momentum. This is what was alluded to in Chapter 9 when discussing Arthur Compton's experiment with X-rays and their frequency changes upon interacting with atoms. Photons have one unit of angular momentum. They have s equals 1. And so the law of conservation of angular momentum requires the total angular momentum of the initial state, molecule plus photon, must equal the total angular momentum of the final state, the molecule after it is absorbed or emitted of the photon. The law of conservation of angular momentum thus requires that the absorption or emission of a photon must be accompanied by the change of the J quantum number by 1, either an increase of 1 for absorption or a decrease of 1 for emission. One can write the following quantum mechanical rule of selection for rotational transitions. Delta J is equal to plus or minus 1, equation 14.8, where delta J refers to the change in the J quantum number for the rotational transition, star. In some circumstances, such as odd electron molecules like NO, delta J is equal to 0 is allowed, but we do not consider these here. This is for an ideal process. Under real conditions, this selection rule is not strictly adhered to, but variances from equation 14.18 are rare, and such transitions are only weakly absorbing or emitting, and so practically unnoticeable. Equation 14.18 therefore defines allowed rotational transitions. Other transitions where delta J is different from plus or minus 1 are forbidden. Linear molecules also have a z component to their angular momentum quantized. And if their total angular momentum is changing by 1 unit, then that unit may be in the z-axis. But then again, it may not. So, the m sub j quantum number might either stay the same or change by 1 unit. Therefore, the selection rule for m sub j is written delta m sub j is equal to 0, plus or minus 1 for linear molecules. Equation 14.19. We've already seen that symmetric top molecules have a second quantum number k used to define the quantized figure axis component of the angular momentum. Interactions of the light field with the molecule's dipole, which must lie on the figure axis, is such that the electromagnetic field cannot change the molecule's rotations with respect to the figure axis. Therefore, the quantum number k is used to define the selection rule. Delta k is equal to 0. Equation 1420. Section 14.6, Rotational Spectroscopy. Now that the selection rules have been established, the energies of transition can be determined. We want to determine delta E, the change in energy between rotational states involved in transition. For now, we will express delta E in terms of units of energy, usually J. For a diatomic or linear molecule, delta E in a rotational transition is difference between energy of two adjacent states. For absorption, the transition can be labeled as E of J goes to E of J plus 1. And the difference in energy can be given by the difference between the final and initial states. Delta E sub E of J going to E of J plus 1 is equal to E of J plus 1 minus E of J, which is equal to J plus 1 times J plus 1 plus 1 times H cross squared over 2I minus J times J plus 1 times H cross squared over 2I. Delta E sub J, delta E sub E of J going to E of J plus 1 is equal to 2J plus 2 times H cross squared over 2I, which is equal to J plus 1 times H cross squared over I. Equations 14.21.